Now wait, don't run away. This is not a video about boring definitions, and most importantly, it's not focused on the IC notation of voltage alone. Notations are more of a side dish here. This is a video that links the definition of voltage, in whichever notation you want, to its application in circuit theory. Here I am going to show you when voltage reduces to its potential difference component alone, and most importantly, where voltage can be treated as if it were a path-independent quantity, just like potential difference, even in the non-static case. And if you stoically resist until the end of the next video, you will also get a glimpse of how that where lies at the foundation of Kirchhoff voltage law, KVL, in lumped circuit theory. As usual, I will assume a stationary setting with slowly varying fields in the context of quasi-statics, which covers most, if not all, the cases where you would use a voltmeter. You can now kiss Kansas goodbye, because we are about to leave the boring parts behind while heading for the more stimulated applications of electromagnetic theory to practical circuits. But first, sorry about that, I still need to give you a brief reminder of the definitions of voltage, scalar potential difference and induced voltage that you are going to use, just to make sure we are on the same page. And also because I know you are not going to watch my other boring videos on this topic. This is one of the last videos in which I will show both notations, US and IEC, before fully adopting the US notation, that is also used in UK, France, Spain, Italy, and so on. I do this for completeness and also because I'm going to rely on the authority of Electropedia, the free online reference maintained by the IC, to validate the definitions. In short, we define voltage along a path between 2 points A and B as the work per unit charge done against the total electric field E when going from A to B, while the IC defines it as work per unit charge done by the electric field when going from B to A. These two equivalent ways to define voltage differ only in the sign of the integral and the orientation of the integration path, and they both give the same numerical value. The IC German notation uses the symbol U and puts the initial point first, as in U sub BA, while the US notation uses V and puts the final point first, as in V sub BA. Maxwell's equations tell us that voltage is the sum of scalar potential difference and induced voltage, as shown here. Even if voltage can reduce to or behave like a potential difference, you should resist the urge to consider these two quantities to be the same. They are not. The scalar potential difference, that is the Coulombian component of voltage that is ascribed to the irrotational part E coul of the electric field produced by the surface and interface charges, is given by the line integral of E minus dA in dt, or E plus dA in dt. The potential function, phi or V, pick your convention, depends on the coordinates of the endpoints A and B alone, regardless of the path joining them. Potential difference is the actual difference between the values assumed by the potential function at the extremes of the path. This also means that, by its very nature, the potential difference goes to zero on any closed path, since that would mean having B equal to A and therefore phi of B equal to phi of A. The other component of voltage, the solenoidal one associated with changing magnetic fields and the corresponding induced electric field E induced, is what we call induced voltage. It is in general path dependent, and it is given by the corresponding integral in terms of the magnetic vector potential A, as shown here. This component of voltage assumes a special meaning when the path gamma is closed and links a variable magnetic field. This non-zero quantity, called loop voltage by the IEC, corresponds to the electromotive force of electromagnetic nature and will be dealt with in another video. Here is a legend to help you decipher the figures in this video. This is a snapshot at a given time t of the time-varying fields and voltages. The gray area is the cross-section of the region of space where the magnetic induction dB dt is relevant. The tiny black vectors represent the induced electric field component alone at a given instant in time. Remember that we are dealing with time-varying fields. If we consider sources with sinusoidal varying fields, we should imagine these vectors to alternatively change orientation at the operating frequency. The induced electric field is responsible for the discrepancy between voltage and scalar potential difference. Its value can be significantly large outside of the sources of magnetic induction, that is, it can be large where the dB dt is negligible or even zero. The yellow dashed lines are the paths of integration for the voltage line integrals. These paths represent the part of the measurement loop along which the probes and leads of an hypothetical voltmeter lie. Path orientations will always be shown using our convention, from lower voltage to higher voltage, and not the German one. Let's revisit the concept of potential difference from a different angle. As usual, we start from the formula of voltage as sum of scalar potential difference and induced voltage, shown here in both notations, ours and IEC's. We already know that potential difference is a component of voltage, and in the static case, when all time derivatives are set to zero, voltage is everywhere equal to scalar potential difference. And let me stress that since we are assuming no field is changing in time, everywhere means in the entire universe. We can relax this condition quite a bit by considering that the minus the Eind term in the line integral is the induced electric field E induced. So the induced voltage integral can be considered approximately zero when the induced electric field has negligible magnitude. This happens either when the magnetic field is very slowly changing with time, or when the quasi-static source is sufficiently far away from the circuit. The last part has more to do with the where than the when, so it will be properly dealt with in the next section. As a sneak preview, look at this figure, where the induced field produced by an infinitely long solenoid is shown in the form of a vector plot. This field extends outside the perimeter of the generating coil, even if there is neither magnetic induction dB dt nor magnetic field B there. The induced electric field varies in magnitude inversely proportional to the distance r from the source, so the farther the generating coil is from the circuit, the weaker is the field. In the context of quasi-statics, there are no antennas, and the faraway source is kind of like no source at all. But let's go back to the acrostatic case and let's see what the formula tells us. If we set the time derivatives to zero in the expression for voltage, we get the following identity no matter the path of integration. In the static case, when the Eind dt is set to zero, voltage reduces to potential difference everywhere. Of course, the same happens in the IC notation, where U is used for voltage and V is the scalar potential. This notion of path independence of voltage when the electric field is irrotational, because the dB dt is zero in our perceivable corner of the universe, is stated as a footnote in the definition of voltage that can be found on the IEC website. obviously with the usual different choice of symbols of the Teutonic notation. We have already seen how the order of the letters in the German notation is consistent with the order of the letters in the subtraction of the integral values, while in our notation we had to put VBA in quotes because the letters are inverted. Using capital BA instead of lowercase ab to make it more similar to our notation, we can rewrite the previous expression as UBA equal to VB minus VA. And the reason for the correct ordering of the letters can be seen in the following formula, where we have plus integral from B to A of minus the gradient of V dot dl, which becomes minus the value of V from B to A, which is minus VA minus VB, which becomes VB minus VA. Not only this is perfectly analogous to the potential difference in our notation, which is written as phi B minus phi A, but we also get the same order of the letters because of the double inversion in sign and path orientation. In our notation, V gamma from A to B is equal to minus the line integral from A to B of minus the gradient of phi dot dl, which becomes plus the value of phi from A to B, which is equal to phi B minus phi A, while before we had VB minus VA. I'm not going to show the equality of both quantities on the same line because the commonality of the symbol V to represent different quantities in the two notations would only cause confusion. Okay, so if all the fields we can perceive around us appear to be static, voltage becomes equal to potential difference, and as such it has to be a path-independent quantity. In other words, in electrostatics and stationary electrodynamics, there is one and only one value of voltage between 2 points, and that value is equal to the scalar potential difference. In quasi-statics, the above rule holds approximately true only if all the sources of magnetic induction dB in T are sufficiently slowly varying or sufficiently far away that their induced electric field E induced becomes negligible. Now you might say, hey, wait a minute, I have personally measured potential differences in circuits that were either very close to sources of magnetic induction, like transformers. If not directly powered by them, their induced electric field could not possibly be negligible in the space occupied by the circuit, and I never saw any path-dependent multivariate mumbo-jumbo sorcery. Well, believe it or not, what you measured was not the scalar potential difference, but voltage. In fact, in selected limited regions of space, voltage can behave exactly like a potential difference, and in many instances the numerical discrepancy can be so small that we pretend not to see the difference. Let me explain. Let's see where voltage behaves like a potential difference. We know that when there are significant time-varying magnetic fields near or inside the circuit or its magnetic components, voltage becomes in general path-dependent and hence multi-valued. Note that I said in general. It is important to understand that this formula does not necessarily imply that voltage has to be different on every single path joining 2 points on the circuit, or in other words, be everywhere path-dependent and never representable by a single valued function. The integral inside these parentheses can be path-independent on all possible paths belonging to a selected safe region of space. Whether this is the case or not depends on the presence or absence of a time-varying magnetic field in the area of interest. As a matter of fact, for most circuits, it is possible to find a region of space that envelops the circuit path gamma and inside which voltage has the same value for all possible paths between 2 points. And by most circuits, I intend all the circuits you will find in the vast majority of electric and electronic circuit textbooks. In what follows, I am going to make some fairly general consideration, so I'm going to set aside the IC definition for a while and focus on our convention alone. Now we need to talk about sources of magnetic induction first. Man-made sources of variable magnetic fields are necessarily finite in extension, and their quasi-static fields wane with increasing distance. This means that it must be possible to find regions of space where the rate of change dB in dt of the magnetic field produced by these sources is either zero or has a negligible value. For example, in the case of a long, tightly wound cylindrical solenoid, the magnetic field B and its time derivative dB in dt are largely confined within the perimeter of the solenoidal coil and start decaying rapidly on the outside. The ideal case of an infinitely long solenoid with a sheet of current is especially simple to treat analytically, with both the B and the B in dt fields being exactly zero outside of its cylindrical envelope. What we can find outside of it, though, is the magnetic vector potential A and its time derivative, which, apart from its sign, is the induced electric field A induced equal minus dA in dt. How strong this field is depends on how fast the magnetic field changes with time. Notwithstanding this, both of these fields decrease in magnitude with increasing distance, as 1 over r, to the point of becoming negligibly small when sufficiently far away from the source. If you find the idea of an infinitely long solenoid unpalatable, a nearly perfect confinement of the magnetic field B can be attained by a well-wound toroidal solenoid. The magnetic vector potential A and the induced electric field are directed along distorted circles around the core sections, and their magnitude too decreases roughly as 1 over r squared with the distance from the torus. This figure shows the perfectly confined magnetic field lines for a toroidal sheet of current along with a slice of the field lines of A curling around them. For clarity, I have not been showing the lines of A inside the core. Just like in the case of a finite solenoid, loosely wound toroidal solenoid will have most of its magnetic field B and magnetic induction dB in dt confined within its core or windings boundaries, while the A and dA in dt fields extend on the outside and are bound to diminish with distance. To avoid unnecessary complications, I will try as much as possible to employ idealized sources where the confinement of the B and the B in the T fields is total, so that they will be clearly represented by portions of space with well-defined boundaries. In two-dimensional sections, they will be represented by gray shapes with crosses and pointed circles to represent the orientation of the field. In the next few figures, I will be adding a diffuse blue haze to represent the rapid decay of the magnetic induction field immediately outside the windings. Note that, unlike the magnetic induction field dB in dt, the induced electric field E induced equal minus dA in dt extends well outside the core where the magnetic field is confined, and it can still be significantly different from zero where dB in dt is zero. As we know from the general formula for voltage, this field is responsible for the discrepancy between the values of voltage and scalar potential difference. Make sure you understand the difference between magnetic induction, the B in the T, and induced electric field minus the A in the T. If you are familiar with vector calculus, Faraday's law, the curl of E equal to minus the B in the T, tells you that the electric field curls around the field lines of magnetic induction, the B in the T, just like the magnetic vector potential A field lines curl around the lines of B. The curling of A and E induced starts in the region where the B in the T is non-zero, but doesn't stop there and extends in the space around it. From a practical point of view, we observe that the range of influence of finite sources is in itself finite, even in real devices where a fraction of the magnetic field B and this magnetic induction field, the B in the T, leak from the source's premises. In the quasi-static approximation, where radiation is not allowed, these fields become progressively weaker the farther away we are from the source. It is therefore reasonable to expect to be able to find parts of the universe where the magnetic induction, the B in the T, of all these man-made sources, be they linked or not by our circuit, become so small that it can be neglected for all practical purposes. When the components are well designed, flux leaks are kept to a minimum, and the regions where we can still perceive a relevant B in the T field are closer to the devices than you might imagine. In fact, in most cases, all we have to be careful about is to avoid getting inside the magnetic components with other parts of the circuit, or going around them with our measuring probes. I will use the term forbidden zone as a shorthand notation to denote these regions of space. The forbidden zone of an infinitely long cylindrical solenoid is the area that includes the solenoid itself. Ideally, the field is entirely confined inside the coil and extends a bit on the outside depending on how long and how closely wound the solenoid is. The forbidden zone around a toroidal solenoid is an envelope containing the solenoid and the donut hole inside it, so that by just staying outside of it, it will be impossible to link any net flux. The cases of relevant flux leaks, and even more so those in which the circuit itself is generating an appreciable variable magnetic field of its own, will be dealt with in a separate video. Now, the absence of any relevant dB in the T, ideally none at all, is an essential trait of what I call zones of voltage uniqueness, or for brevity, safe zones. Now, be aware that this is not a standard or shared denomination. I just made it up to avoid lengthy repetitions when I want to indicate a region of space subject to the following two conditions. 1. It does not include any forbidden zone, that is, areas of space where the magnetic induction, the B in the T, is different from zero. And 2. None of the infinitely many closed paths it contains are allowed to encircle a forbidden zone. At first, these two conditions appear to be redundant, but they are not. We will presently see that there is a particular geometric constraint a safe zone needs to satisfy if you want both conditions to be satisfied. Here is an example of safe zone that should help clarify what I mean. Being inside a safe zone brings massive simplification in the analysis of electric and electronic circuit, because a safe zone is a region of space where the electric field happens to be conservative even when there are time-changing magnetic fields nearby. The most relevant consequence of this local conservativeness is that voltage inside these zones does not depend on the path of integration. Note that what makes a zone safe is the impossibility to link an appreciable magnetic induction field, the B in the T. The B in the T is either 0 or almost 0 in all points belonging to the zone, and it is not possible to go around any external dB in the T region without crossing the safe zone's boundaries. And here is where the geometric constraint comes in. Consider a monolithic region of space with a hole in it. If there is a magnetic induction field dB in the T inside the hole, the forbidden zone does not belong to the region itself because it is external to it, and yet it would be possible to find a closed path that goes around the forbidden zone while staying entirely inside the monolithic region. This is something that we cannot accept if we want all possible paths not to link any dB in the T contribution. In fact, the integral of the electric field along the yellow closed path is the circulation of E, the total electric field, and Faraday's law tells us that it must be equal to the flux of dB in the T in the forbidden region, linked by the path. If there is a source of magnetic induction inside the hole, this integral will in general be not zero, and we cannot allow this to happen since the existence of closed paths with non-zero circulation is what prevents voltage to be path independent. We must therefore impose the condition that a safe zone cannot have any hole. Technically, we must require that a safe zone be simply connected, a mathematical term that roughly means one piece without holes, as shown in this figure. For reasons that will be clear later, you might prefer to see the shapes in this way. Of course, the relevance of not linking any dB in the T is a direct consequence of our aspiration to a path-independent, single-valued voltage along any possible path within the zone itself. Once we have identified a safe zone that contains our circuit, provided one exists, we can be sure that voltage between any pair of points of the circuit would not depend on the path, at least as long as the path is entirely contained within the safe zone. I will get into boring details in later videos, especially that on how the voltmeter senses the induced voltage, and even more so in the video dedicated to KVL. It's trivial to identify safe zones in DC circuits where the dB in the T zones are all external to the circuit itself and are reasonably self-contained. But what about AC circuits, which rely on magnetic induction to power their generators, or even general dynamic circuits that include inductors and magnetic sensors? If the magnetic induction region is part of the system, how can we possibly find a region of space where the electric field happens to be conservative and voltage to be single-valued? Well, it turns out that it is usually, but not always, possible to do it, and actually there is also a very simple way to do it. The crucial part is that it must be possible to define a circuit path gamma that does not enclose any relevant variable magnetic field region. When the circuit has to link one or more regions with a changing magnetic field, the only way to do this is to exclude them from the circuit's interior by confining them inside magnetic components. Instead of following the conductor inside the magnetic components, the circuit path jumps in the space between terminals, leading to an imaginary closed line that strings together all components and does not link any forbidden dB in the T zone. The magnetic components interact with the rest of the circuit by means of the voltage and current as seen from the terminals. In particular, the voltage that can be computed by integrating the electric field along any path between the terminals inside the safe zone that includes gamma can be considered to be single-valued and takes the name of terminus voltage. All variable magnetic flux regions must be off-limits for both the circuit path and the integrating paths that represent the instrumentation leads part of any measurement loop. From a practical point of view, Whenever magnetic components such as the coils in AC generators, transformers, and toroidal inductors are present, we can prevent the interception of unwanted magnetic flux by simply not entering their enclosure with neither the circuit's conductor nor the instrument's leads. In the case of the shown circuit, it means avoiding crossing the rectangular boundary of the transformer. For certain types of inductors, we must also pay attention not to go around them with our probes, because doing so would link a net non-zero magnetic flux. To see why, look at the blue path in the figure. From the perspective of the circuit path gamma, shown here in red, we need to bypass each magnetic component by introducing a jump at their terminals in such a way that the amended circuit path will not link any relevant dB in the T field. These will ensure the existence of a safe zone containing the path itself such that voltages computed along any of the paths contained therein will be path independent. I will get into the details why the jump can be considered a valid part of the circuit path in the video about KVL. For now, the key takeaway is that for voltage to be locally single-valued, no measurable time-changing magnetic field must be present in the area of interest encompassing both the circuit path and all relevant measurement loops. Note that in all these circuits I am assuming there is no relevant magnetic induction associated with the current flowing in the circuit itself. In circuit theory terms, I am assuming that the self-inductance of the circuit itself is negligible. It is a very reasonable assumption, shared by a large swath of AC and pulse circuits with small enough currents and low enough frequency, that is, most of the circuits you might encounter in general-purpose electric circuits courses. Okay, so far we have seen that the characterization of safe zone depends only on the magnitude and position of the magnetic induction field, dB in the T. But what about the electric induction field, E induced equal to minus dA in the T? Does it matter somehow? This field can be significantly different from zero throughout the entire safe zone, even where dB in the T is zero. After all, this is the field that is responsible for rearranging the configuration of charge inside and on the surface of the conductors that reside in the space around the source. The surface and interface charge displaced by this field will in turn generate the Coulombian field E cool, responsible for the scalar potential difference component of voltage. It is only when at least one mesh of the circuit links the source of magnetic induction that a current can circulate. On the other hand, when the source happens to be external to the circuit, the only effect is a displacement of charge resulting in the electric polarization of conductors and the nullification of the total electric field inside them. Remember, these figures are snapshots at a fixed time t. The quasi-static time evolution is a sequence of these snapshots, one after the other, with the magnitude and sign of the field changing with time according to the time evolution of the exciting current in the primary coil. In the next video, we will see in what ways a measurable induced electric field within the circuit's premises can affect the values of voltage and scalar potential difference, or rather, in which proportions voltage is partitioned into its scalar potential difference and induced voltage components. For the moment, I just want to make clear that regardless of the position of the sources, be they linked or not, the presence of the induced electric field does not prevent us to find a safe zone when such a zone exists. It is worth noting that inside the safe zone the induced voltage becomes path independent as well. Incidentally, this means that it must be possible to reproduce any portion of a solenoidal field configuration within a safe zone by the irrotational field of a suitable quasi-static distribution of charge. There is a very simple analytically solvable example, and if I don't die too soon, I might even make a video about that. For now, let's see a few examples of safe zones in DC and AC circuits. This figure shows a battery-powered circuit surrounded by bounded sources of magnetic induction, external long solenoid and an external toroidal transformer that keep the dB and dt zones confined within their boundaries. The circuit sits in a dB dt free zone where the electric field is locally conservative, even if it is still immersed in a significant amount of induced electric field not shown for laziness. As an aside, since with the exception of minor flux losses, a good transformer keeps the entire variable magnetic field confined within its finite core, all we have to worry about in order to avoid cutting net flux is to avoid paths that get inside its enclosure. In fact, if we consider paths that go around the entire transformer, the net flux linked will be zero. What is interesting is that we can find a region of space where the electric field is conservative even when changing magnetic fields are linked by paths of the circuit. These paths end up being what in the lumped circuit model we would call lumped components. This is true not only when the linked sources are so far away that their induced electric field would be near zero where the circuit is located, but also, and perhaps surprisingly, when the source is close enough to the area occupied by the circuit to introduce a significant amount of induced electric field in the dB dt free zone, like in this picture. Or like in this more familiar circuit where the power source is a more conventional transformer. Here, neither the primary winding nor the overall induced electric field are shown. So, if we can find a monolithic chunk of space with no holes, where there are no changing magnetic fields, the total electric field there will behave as a conservative field. Since the Coulombian electric field is conservative by definition and E tot equals E Coulombian plus E induced, and that is conservative, it follows that E induced has to be conservative as well, at least within the safe zone. You might need a minute to realize that this has to be true. But anyway, if the circulation of E induced is zero on any closed path within a simply connected region of space, the induced voltage between any 2 points in this region will assume the same value regardless of the path joining them. This implies that voltage, which in this region of space becomes the sum of two path-independent quantities, ends up behaving like a potential difference, even if it is not the scalar potential difference component alone. Okay, so when the total electric field E is conservative, and the induced field is not identically zero, it means that E induced has to be conservative as well. But how can it be so? After all, isn't E induced the solenoidal, non-conservative part of the total electric field? We can see it going in circles around the sources of magnetic induction. How could that current field possibly be conservative? Well, just like the total electric field E induced is only, quote, locally, unquote, conservative, in the sense that its circulation is zero along all closed paths contained in a simply connected region of space that does not include its magnetic induction sources. Can we explain this by just looking at the fields? Well, yes, we can explain this requirement by observing that the contribute of the induced electric field E induced to the voltage path integral will always cancel out on all closed paths that do not go inside or around the source of dB dt. We can intuitively understand why this happens by directly looking at the field in the special case of an infinitely long circular solenoidal source. In this case, the induced field has a simple analytical expression, and we can analytically compute all path integrals to show how only linking the source affects the results, while not linking it leads to a cancellation of contributes on oppositely directed paths. These figures are just a preview of what's coming up next, and I will get into the nitty-gritty mathematical details in one of the next videos, but this is the reason why the only quasi-static magnetic fields that can affect voltages and currents in a circuit are those linked by the circuit itself, and in particular by its magnetic components, while those on the outside can be safely ignored as far as voltage and not scalar potential difference is our concern. Well, unless you get too close to a neutron star or to a magnetar and the induced electric field starts to strip electrons from all conductors. In summary, when dealing with electric circuits in the presence of variable magnetic fields, we have two main fields to worry about: the magnetic induction field dB in the T and the induced electric field E induced equal to minus dA in the T. And both of them will eventually die out sufficiently far away from any finite source. But only one of these fields, dB in the T, is relevant in terms of its effects on the voltages and currents in our circuit, and also as far as the uniqueness of voltage is concerned. As we will presently see, the induced electric field can only alter the partition of voltage into its scalar potential difference and induced voltage components. In the end, this is all you need to remember. In a simply connected zone where dB in the T is zero, voltage is path independent, but only where E induced is also zero, voltage becomes equal to the scalar potential difference. That's not too much information, right? It's going to be easy to remember it. I'll do my best trying not to dampen your spirits by telling you that depending on where the forbidden magnetic induction zones are with respect to a given circuit, it might not be possible at all to find a safe zone that includes the circuit path. Or, equivalently, it might not be possible to amend the circuit path in such a way as to exclude all dB in the T zones from its interior. Translating the simply connected dB in the T mumbo-jumbo into practical terms, in order to have a single valued voltages for every pair of points in your circuit, you must be able to find a circuit path that can be shrunk into a point without cutting any time-varying magnetic field lines. Think of the circuit path as if it were a rubber band that can shrink with heat, along with anything connected to it, with the sole exception of the dB in the T zones. The magnetic induction sources act as solid objects that will prevent the rubber band from shrinking any further. If you think about it, this rule explains why we need to introduce jumps between the terminals of all magnetic components. These jumps allow us to exclude the forbidden zones so that the modified or amended circuit path will end up being entirely included in a safe zone. When the circuit lays on a two-dimensional surface, the rubber band method makes sure that all paths containing inside the area delimited by the circuit path will give single-valued line integrals of the electric field. We can consider this a minimal area in which voltage behaves like a potential difference. How much this area can be extended outside the circuit path boundaries depends on the position of the external sources of magnetic induction. This local conservativeness, let's call it this way, in all simply connected parts of space free from dB in the T also explains why, when you are measuring voltage with a voltmeter, You only need to be concerned with the changing magnetic fields linked by the actual measurement loop and not those outside of it. Let me reiterate that a measurement loop is a closed loop formed by the branch of circuit you want to measure voltage of and the path formed by the voltmeter, its leads and its probes. It is shown by a dashed yellow line running inside the voltmeter's lead and going through its internal input resistance. Note that, as shown here, there can be multiple measurement loops when multiple branches of the circuit have the same endpoints in common. To avoid cramming too much stuff in the following figures, I will rarely show the voltmeter and I will represent the measurement loops with the oriented dashed yellow path alone, indicating whenever possible the numerical value of the line integral along that path. I will leave it to your imagination to place a voltmeter and its leads along one of these lines. It is trivial to find measurement loops that do not link any magnetic induction dB in the T when the circuit is reasonably far away from any perceivable variable magnetic field source. For example, this is a circuit where all voltages are path independent, so that we can think of voltage as a quantity defined across 2 points, even when the source happens to be closer to the circuit. As long as it is not linked by the circuit path, it is not particularly difficult to consider voltage as a single value quantity. All we need to do is to avoid cutting through or going around the external dB region with our yellow paths. What might surprise you is that it is still possible to consider voltage to be single-valued even when the changing magnetic field is linked by the other parts of the circuit you are probing. In this case, the magnetic induction can be responsible for voltages and currents in the circuit. For example, an AC generator or a transformer or even a magnetic sensor. But as long as our measurement loops do not include the forbidden dB zone, they will not interfere with the measurement. There are circuits, though, where the source of variable magnetic field is positioned in such manner that it is practically impossible to identify a circuit path that does not include it. When this happens, there will always be branches of the circuit that will have the same endpoints in common, but will have different voltages along them. To add to the confusion, it might still be possible to find a consistent and different single value for both voltages in suitable but different safe zones. I will stop here for the moment because otherwise this video would be 1 hour long and some of you might not make it to the end alive. The bottom line is, if we want to treat voltage as a path-independent quantity, we have to make sure that both the circuit path and all measurement loops of interest reside in a simply connected region of space that does not contain or link any time-varying magnetic fields. In the next video, I will get into a little more detail in what makes a zone safe and how the sources of magnetic induction alter in different ways voltages and scalar potential difference in a circuit. Let me reiterate that when there are sources of magnetic field that are either sufficiently strong or sufficiently near the circuit, does not matter if they are linked or not, voltage is not equal to scalar potential difference. This is not just a mere mathematical curiosity. If you think you have been measuring scalar potential differences between the points of a circuit that either links or simply sits near a source of magnetic induction, the B in the T, you are in for a surprise.